Okay, let's get a little help with scientific notation. So scientists need to express small measurements such as the mass of a proton, at the center of a hydrogen atom, which is this many zeros, 1673 kilograms, and large measurements such as the temperature at the center of the sun, which is 15, and this many Kelvin degrees. To do this conveniently, they express the numerical values of small and large measurements in scientific notation, which has two parts. The two parts are a number in which only one digit is placed to the left of the decimal, so this number is number 1 through 9 only, and an exponent of 10 by which this number is multiplied. So this could be 10 to the second. If it's 10 to the second, that means 10 times 10, right? If n is 2, then that would be 10 times 10, which is 100. So then it would be whatever is the first number times 100. And if it, let's say, was a negative number, let's say it was 10 to the negative second, that's the same as 1 over 10 times 10. So that's the inverse of 10 to the second, which is 1/100th. So that would be whatever this number is times 1/100th, or 0.01. So really what we're going to do is look at the next part, and we're going to move the decimal point left or right based on what the exponent says. So if you have the number 1234.56, each time the decimal place is moved 1 to the left, you have made this number look smaller by a factor of 10, and so you need to increase the original number times a factor of 10. If we're going to move it one more to the left, then we need to multiply it times another factor of 10, so it's now 10 to the second. If we move it one more time to the left, then we need to multiply it times another factor of 10, so all of those 10s together, 3 10s, is 10 to the third. And so you need to keep moving the decimal over until you get it behind the first digit that's not 0, because remember, the first digit can only be 1 through 9. And the number of times that you move it to the left is equal to the exponent, or the power of 10. And so what this really is 1.23456 times 10 times 10 times 10, which is 1,000. Or move the decimal over 3, because that's what happens when you multiply something times 1,000. Or 1 decimal place for each 0, for each 10. So each 0 in the power of 10. So we have 1 and then 2, 3, 4.56. We moved it 1, 2, 3. 1, 2, 3. There we go. 1, 2, 3, 4.56. So the final number is equal to the original number. It's just written so that the first number looks smaller than it did before, but when you multiply it back times the 10 to the third, it really equals the same original number. Negative exponents make a number smaller. So if you have 0.00657, each time the decimal place is moved one place to the right, so move this to the right one place, we multiply it times 10 to the negative first. So remember, 10 to the 0 is 1. So if we just multiply something times 10 to the 0, it doesn't change. And if we decrease the exponent by 1, that makes the exponent -1. So every time we move the decimal place to the right, we add a negative exponent to 10. And then if we move it another place to the right, now it's going to add another negative exponent, and another place to the right, it's going to add another negative exponent. And so now we have 6.57 times 10 to the negative third, which is 6.57 times 0.001, or 1 over 10 to the third, which is 10 times 10 times 10, which is the same as 1/1000th. 1 over 1,000 is 1/1000th, which is 0.001. And so if you multiply 6.57 times 0.001, to get the number back, you would have to move the decimal 1, 2, 3, and it would be 0.00657, which is the same as it was at the beginning. So this number is the same as this number. Okay, it's just a way to take the zeros out and make the number more manageable. This is a way to take the large number of digits before the decimal point out and make it more manageable. Now, these numbers aren't super huge, and there isn't a super huge number of zeros, but as you can see up here, you definitely would not want to use all of those zeros, and these zeros here in 15 million might not be too bad. But let's think about the fact that if we have an atom having this small of a number for its mass, it would take an equally large number of zeros to tell how many atoms it would make in, let's say, 1 kilogram or a gram, or an amount that's big enough for us to see. Okay, so we're going to practice a little bit. Remember that when the number is greater than 1, we have positive exponents. And when the number is less than 1, which means decimals, we have negative exponents. And so express each of the following numbers in scientific notation. So the first thing you do is remember that the decimal point that you cannot see is always at the end of a number. So you move it 2 to the left, and it's 2.3 times 10, and we moved it 2, and the number's greater than 1, so it's positive. So remember, you can always take this and check your answer. 2.3 times 10 times 10 definitely is 2.3 times 100, so it's 230. If you can't get the same answer back that you started with, you probably did something wrong, like maybe used the wrong exponent, or used the wrong sign on the exponent. And let's go, and notice we just dropped off the 0, and that's fine. So if it's at the end or the beginning, we can drop them off. It's in the middle, of course, we can't drop them off. So 5,601, move the decimal over after the first digit, 5.601, times 10, is it going to be positive or negative? This number is greater than 1, so it's going to be positive, and we moved it over 3, so it's going to be times 10 to the third. And if 5.601 times 1,000 is 5,601, we did it right, right? 5.601 times 1,000 does equal 5,601. Okay, let's go down to letter E. Letter E is 2/10, right? How do you write 2/10 as a decimal? 0.2. And so in this, you have a number that's less than 1, so the exponent's going to be negative. Okay, so we're going to move the decimal to the right by 1, so that's going to be an exponent of -1. And this is 2 times 1/10, which is 2/10, which is what this is. You could even write 2 times 1/10, which is 2/10, which is exactly what they gave us. It's also the same as 0.2, remember. Okay, let's do letter F. So 0.45013, we want the decimal to be after the first non-zero digit, so we're going to make it 4.5013, and we only moved it over 1 decimal place to do that, and the number is less than 1, excuse me, and so that is a -1 exponent. I'm just going to go down here and do one more, letter H. We need to move the decimal over to after the 2, so it's going to be 2.6, and we're going to count 1, 2, 3, 4 places, and it's a small decimal number, so it's going to be 10 to the -4th. And then down at the bottom, I'm just going to do one of these. So this number 2A, the speed of light in a vacuum is 299,792,458. By the way, in science, many times instead of putting in commas, they just leave spaces. In many countries throughout the world, they don't use commas. They actually use commas instead of decimal points, and it can get very confusing. So it is better just to leave a space. If you see a space, it's the same as a comma. It just helps you see how many sets of 3 numbers we have. It helps us count, helps us tell how big or small the number is. Okay, so speed of light in a vacuum, we need to move the decimal in a number greater than 1. It's at the end, and we need to move it all the way here. And that is 1, 2, 3, 4, 5, 6, 7, 8 places. So 2.997992,458. We can't leave off any of those numbers. We're not rounding it off for any reason. We're leaving it the same, but we moved it 8 places to the left, so we need to have a positive exponent because that's a larger number than 1. And then letter E, radius of an argon atom, right here, we're going to move the decimal point so that's after the 9. And so we're going to move it by 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 places. So it's going to be 9.8 times 10. And it's a very small number, so we're going to use a very small exponent, negative 11. And don't forget your meters here and your meters per second here. If there are units there, you have to keep the units in it because it's a measurement. Okay, so stop the video and work on the rest. And then come back to the video again and check your answers. Okay, so let's go over the answers to the rest. On this one, we're going to move the decimal point to after the first one. So it's going to be 1.41 times 10 to the 1, 2, 3, 4, 5, 6, 7. 56 million, I would write that out first. 56, 1, 2, 3, 4, 5, 6. And we're going to move the decimal point 3, 6, and 1 makes 7. So that is 5.6 times 10 to the 7th. Letter G, 0.089. We're going to move the decimal after the 8, 8.9, and this is less than 1, so this is times 10 to the negative second. And then this one's going to be 6.98 times 10 to the negative 1, 2, 3, 4, 5, 6, 7. 12,000th is 12 over 1,000. That is 0.012. So that is 1.2 times 10 to the negative second. Down here, number 2, 2b, number of seconds in a day. Move the decimal 1, 2, 3, 4. 8.64 times 10 to the 4th seconds. 2c, mean radius of the Earth. 1, 2, 3. 6.378 times 10 to the 3rd kilometers, and the density of oxygen gas at 0 degrees Celsius and pressure of 101 kPa, which is kilopascals, and we'll learn that later, is 0.00142. So I'm going to move the decimal 1, 2, 3, so 1.42 times 10 to the negative 3rd grams per milliliter. And the next page, we just need to learn our calculator. We're going to learn to use our calculator in class, so I'll come back to that later.